I'm discussing three-dimensional case, which of course is relevant for morphogenesis, but mathematical results for other dimensions sometimes are the same or not, right? But at least the formulation would be the same. So the W is evaluated on not as usually we do in nonlinear elasticity, just on the gradient of deformation. So U here going from omega to R3 is the deformation. But on the deformation from which we've taken away certain component, which is understood as the square root, so there is negative sign here, of the Riemannian metric. Okay, so the G is the Riemann metric written in coordinates here on omega, so you can think that that's just a field, smooth one, which the points in omega associate are 3x3 symmetric positive definite matrices. And this G here is related to the prestress on omega. Okay, so G is imposed. For every U, of course, here I need some regularity, right? So W is quadratic, so gradient U better be in L2. So indeed, I'm defining it for U, which is in W12 from omega to R3. That's the regularity of my deformations. That's the energy, that's the key persona in my talks. And now we want, right, what do we want? We want to understand what's the infimum or what's the minimum or E of E over U's deformations as indicated before. Okay, so want, what is this? How big it is? What can I say about the minimizers? What can I say about the asymptotic properties of those minimizers or infimizers in various scenarios? Okay, I will make that precise. So we checked yesterday the dichotomy, even sketched the proof. We gave a extensive discussion of this result. So there's a dichotomy either, right? So either the infimum of E is strictly positive, okay, bounded away from 0, 5 or 1. That is, you cannot, for any deformation, you cannot go below that positive number. Or, in fact, if that's not the case, if infimum is 0, if you are able to get by some deformations as close to 0 as you want in your energy, this means that the situation is entirely trivial. So or means that actually the minimum of E is 0. And argmin of E, continue here, is unique up to rigid motions. And smooth. And all this means that in fact your metric, your original metric, was flat. So the Riemann curvatures of G was entirely 0 in omega. It's very, very strong assumption. Okay? So unless you have this extremely strong particular property of G happening, again, this means that we are in 3 dimensions, 6 partial differential expressions involving 2 derivatives of G must be entirely 0 in omega. Okay, so that's a very residual situation. So if that is not true, again, if that is true, then by a smooth, automatically unique, change of variable, the situation is trivial. This is like nonlinear elasticity with no force at all, nothing is happening, okay? And if that's not true, then there is a residual, there is a barrier, energetical barrier, okay? You cannot pass a certain positive number, no matter what, even for, you see those deformations. I'm not assuming they are smooth, I'm not assuming they are orientation preserving, I'm not assuming anything. They are just W12, which means that their gradient is integrable with second power. So you could think you can do a lot of things, right? You can do a lot of local construction, sort of kind of origami, or, right? You can do lots of different things, but no, you can't pass a positive number. Okay, so that's the beginning of the story. That was the first lecture, and today, so actually, let me mention there is an open problem in this context. So at this level of generality, quantify this infimum. So the expectation is that infimum, that this infimum of E should be bounded up to a constant. This should be basically like an appropriate measure of the Riemann curvature, right? Riemann curvature 0, if and only if that infimum is 0. So, okay, for various other reasons I'm not discussing here, it's expected that this infimum is like, say, Riemann curvature of G, appropriate norm, which naturally should be H minus 2, and here square, and it should be also bounded from below by another constant, okay, times the same thing. Okay, so that's still an open question to prove that, right? That is to check the state check to prove this you know, statement. So sort of that's the statement in the kernel, and I want to now quantify how big this infimum is in function of how non-zero this object is. But today, what we start doing is we will focus on a topic that's of interest to several of you, and these are thin domains, thin films. So from now on, okay, omega will always be a plate that's a Cartesian product of a two-dimensional set, little omega, okay, times an interval minus h half, h half. So it's a plate of thickness h. H. And h is very small. Okay, so little omega is now a fixed mid-plate set. I'll never vary it in my results, but I will vary the h. In particular, I want to understand what happens when h goes to 0. Okay, so that's because of that, let's call this omega h. So now we have the energy EH. Okay, so that was E. Now I have EH of U will be pretty much the same as before. Now that I integrate on omega h, I'm going to scale by the unit thickness, which is proportional to the volume of omega h. Okay? And here I have my W defined on gradient U, G inverse 1/2. The X, and that's defined for U, which are W12, from omega h to R3. So this is rather than a single energy. In fact, it's a family of non-Euclidean elastic energies which are posed on thin domains. And I want to understand what happens when h goes to 0. In particular, want to understand as h goes to 0, I want to determine the scaling of the infimum of EH, right? So if that metric G is non-immersible, if I am not in that particularly restrictive situation, then for every H, the infimum of H is positive. And it's going to go to 0, we can expect that, thinner and thinner plate, but at what rate? Okay? So this infimum EH is like H to what power? Okay? So determine beta in function or in relation to what's making this problem non-trivial, and what is making this problem non-trivial is the Riemann curvature of G. Okay, so I would expect that if you give me a particular G, not just I expect, I know how to do it, this is what I'm going to teach you, okay? If you give me a concrete G, by looking at its curvature, at its curvatures, I should be able to guess what's the beta. Okay, and I can do that. So in relation to the magnitude of different components of the Riemann curvature. Another interesting natural problem here is what's the behavior of argmin, right? The minimizers of EH. So when H goes to 0, do they accumulate close to, you know, certain deformations of midplate, maybe? I would like, in particular, to see that when H goes to 0, these minimizers become, in the limit, they are getting closer and closer to the minimizers of another residual, dimensionally reduced energy functional that I'm going to call I beta. So what is? Determine I beta. Okay, so these are the 2 points that are of interest to me, and we are going, in fact, so just to anticipate what's going to happen, we will see that the story is completely resolved for beta greater equal than 2 and beta less than 1. The above questions can be precisely answered, can be answered precisely. Yeah, it's just anticipating the results I will show you. So of course the question is what happens between scaling of the infimum of the energy thickness to power 1 and thickness to power 2, and that's virtually from the point of analysis, mathematical theory, that's an open range of exponents.
I have a question for I beta. So I beta, do we know?
No, this is, I will tell you, that's just an appetizer for what's going to happen, okay? I haven't formulated any results. So that's a wishful thinking. I didn't tell you what that is. Wishful thinking is, I would like to know that I only know this EH. I want to understand what happens when H goes to 0, what happens to the minimizers of EH, okay? So I'm going, in fact, to prove a series of theorems. Okay, I haven't introduced anything yet. It's a series of very deep statements that those minimizers accumulate close to minimizers of something else. And that something else will be another energy. I didn't tell you what that is, okay? It turns out that for different betas, you will have different energies. This is all coming, right? That's just to tell you what we want, and hopefully we will get there. Okay?
I had a quick question also
Yes.
related to this. So in principle, this beta would be a function of the Riemannian curvature.
Yes.
Right?
Yes.
But
yes.
when you make
different of various Riemannian curvatures, again, we will see results in this direction, right? So that's what I want. I want to determine beta in relation, in function of different Riemannian curvatures.
Right. So, and when you make this inequality statements about beta, that's going to tell us something fundamental about when you make these inequality statements about beta.
I tell you that for all betas, I know I mean, okay, maybe I just deleted because you are asking about the content of the next 5 hours. We will get that, okay? Let's just, we will see. You will see exactly what I mean by that. Okay, that's the beginning. These are my questions, and we are going to answer all questions that you might have here precisely, I promise. Before we do it, I need to introduce the fundamental concept which allows to find the accumulation points of the minimizers in a sequence of functionals. Okay, that's the fundamental type of convergence in the field of calculus of variations, and it's called the gamma convergence. Okay, so let's do that. So definition. So let XD be a metric space. And we have a sequence of functionals, of functions, but those functions will be like our EHs. Fj, which goes from X to R, possibly extended, plus infinity, minus infinity, okay? A sequence of functions. And we say that Fj, okay, so gamma, it's really capital gamma converges to F, and F is another function from X to R, okay, provided that. Two conditions. Condition 1, condition 2, both of them have to be satisfied in that definition. The first condition is called the lim-inf condition. It says this: for every sequence xj which converges to X, so that's convergence in X, in capital X, okay? That's my metric space in XD. For every second, I have a space here, and on that space, I have my energies. Like here, you can think you have those W1, 2, and on them, on every object, every element of this, right? That's like my capital X, I'm defining EH. Okay? So, first condition, whenever I have a sequence in the base domain of my functionals converging something, then the value of F, this gamma limit, at the limit must be less or equal than lim-inf when j goes to infinity of Fj of Xj. Okay? So if I look at the behavior of Fj along any converging sequence in the base space, then capital F, the gamma limit evaluated at the limit of that sequence, must provide a lower bound for Fj along Xj. Okay, that's the first condition. The second condition called lim-sup condition says that this F provides the best lower bound possible, right? You agree with me that if I have that, then of course F minus 15 is also a lower bound. I don't want F minus 15, I want the tightest bound from below. So that's the gamma, that's the lim-sup condition. It says that for every X in capital X, there exists a sequence, Xj, which converges to X, okay, along which I attain this as equality. Basically, of course, equivalently, it says lim-sup condition. I'm going to write f of x is greater equal than lim-sup as j goes to infinity, fj of xj. But in view of the first condition that's true for any sequence, okay, this means that automatically, right, this automatically means that this f of x equals to the limit when j goes to infinity, fj of xj. This sequence, therefore, is called the recovery sequence. Recovery sequence, right? I can recover the information on f of x via the behavior of my basic Fj sequence of energies, if you want, along that recovery sequence. So that's the definition of gamma convergence introduced, several years ago by Italian mathematician Ennio De Giorgi. If you haven't seen it before, you should be very puzzled. I'm going to make you even more puzzled because I'm going to give you a series of examples that working out these examples, I leave it to you as a homework, okay, which will convince you that this convergence has nothing to do, really nothing to do with any type of convergence that we study in analysis that you might have learned at school, right? So we know uniform convergence, we know pointwise convergence, we know weak convergence, we know convergence in various functional spaces, like in L2, right? The integral of square of the difference between the functions goes to 0. Nothing like this is completely different thing, not a subset or superset of any of those convergences that I just mentioned. Okay, so let's see examples. Example 1, a constant sequence. Fj. So Fj all the time equal f, one and the same function. It does not converge to f in general, right? So constant sequence converges to f if and only if f has a certain property, namely it's sequentially lower semi-continuous. So if and only if, of course, it's, okay, I leave it as a homework. I don't want to waste time, but it's very, very simple. If and only if for every xj converging to x, f of x less or equal than the inf f of xj when j goes to infinity. Okay, so this property means f is lower semi-continuous. Example 2.
Understand how this is compatible with the. I mean, what about the condition 2? Is it?
What do you mean? What about the condition?
So I mean, it's.
That's a homework. I'm not solving it for you now. It's a homework. It's trivial. You will think, you will solve. Okay? Recovery sequence is constant. Xj equals x. Yeah. As I said, it's not a homework. You have to think about it. I have finite time to discuss other things. Okay. Example 2. Take fj and f from R to R. And where f1 of x is defined as, okay, why not square root 2x exponential minus 2x squared minus 1 divided by 2. So this function looks like this. Goes to 0 here, infinity, okay? It passes through 0. It's odd and attains maximum 1 and minimum minus 1 at symmetrically points that are symmetric. Okay, that's f1. And then I define fj of x to be f1 of jx. Okay, so what happens when j goes to infinity? This is squeezed. So clearly fj, we see that fj converge to 0 locally uniformly. Okay, certainly locally uniformly outside of 0. Okay, but Fj gamma converges, that's a notation, to the function f of x, which is 0 if x is not 0, and -1 if x is 0. Completely different thing. Example 3. Oh, maybe example 3 actually here. You can check that negative Fj from example 2, the same negative Fj like this. But negative Fj, in fact, gamma converges to the same thing, not to negative f, to the same f as before. Okay, so in particular, I have, negative Fj plus Fj. Of course, that is 0, so that's really constant sequence 0. 0 is lower semi-continuous, right? So this gamma converges to 0, but it does not gamma converge to the sum of the gamma limit of this and the gamma limit of this, which would be twice f, that is not 0. Here, example 4. Fj, again from R to R, negative cosine Jx. So it looks like this, squeezed. Of course, then there is no, this sequence does not converge pointwise. There is actually no converging, pointwise converging subsequence even. Subsequence of this Fj. But I ask you to check that Fj gamma converges to the constant function that's equal -1. Okay. And example 5. So negative example when I don't have a gamma limit. Define Fj of x as follows. First, a prefactor -1 to power j, so it's going to oscillate +1 -1 on what? You put 0 if x is either irrational or x can be written as k over n for n, which is between 1 and j. And you put -1 otherwise. Okay, so when x is irrational, you put 0, and you get 0 on more and more rational numbers as j increases. In fact, on all rational numbers, right, with the denominator, which is up to j, which is that counter, I'm putting 0. Okay, and -1 otherwise. Of course, Fj converges to 0 pointwise. So after, on irrationals, it's 0 all the time. If you take a rational number, eventually it's going to be on this form. So of course, then I get 0. But gamma limit does not exist. Okay, so these are curious examples which really raise the question, do we care about the gamma limit and why do we care about it? What has it to do with anything? And I already told you there's a fundamental type of convergence in calculus of variations because it allows to detect the behavior of minimizers. We have the following result. Let's call it a lemma. Very easy to show. We will show it, which really reflects the basic property of gamma convergence. So assume that gamma j, that fj's, gamma converge to f as in the definition. And moreover, assume that there exists, so this second assumption can be, it can be expressed in different ways. So I just write one particular way. Moreover, assume that there exists a compact set K. I need some compactness property, compact subset of big X, such that for every J, the infimum of Fj on the whole X equals to the infimum of Fj in K. Okay, so assume that I know that functionals, all functions infimize properly in K. Then, one, the gamma limit F has a minimizer. I haven't assumed that Fj's have minimizers. Okay, I just assume that they have infima. So I assume that F has a proper minimizer. Two, if Xj is an infimizing sequence, so if I know that Fj of Xj minus the infimum of Fj over the whole X, okay, actually goes to 0 as J goes to infinity, then Xj, so these are, okay, and Xj in K, then they converge to, up to a subsequence, of course, they converge to a minimizer of F. So Xj up to a subsequence converges to some X, and in fact, X is argmin of F. And vice versa, 3, for every X, that's the minimizer of F, I can recover it in the limit of approximate minimizers, infimizers of Fj's. So for every X like this, there exists a sequence of Xj's converges to X, okay, such that Fj of Xj minus the infimum over X of Fj converges to 0. Proof? Okay, so let's start with 2. Let's take sequence Xj such that I have this. So let's call this condition star. So let Xj in K satisfies star. Of course, it's a compact set, right? That's why I need something to make sure that they, this approximate infimizers accumulate at some point. So I know by compactness up to its subsequence Xj converges to something, X, and we have that the f of X by the gamma lim inf property is less or equal than lim inf of Fj on Xj, right? But condition star means that this Fj of Xj behave asymptotically the same as the infima of Fj. So this equals to inf fj of xj, sorry, infima of fj. So I'm basically done, but for the future reference, let me write something trivial. This is less or equal, of course, than min sup, then inf of inf fj. And now if I take any y in X, I can find a recovery sequence, let yj converging to y be its recovery sequence. I'm using the property of the gamma convergence. So of course, the infima of fj is less or equal than the value of fj on yj, right? Yj is just some point. So this is bounded by lim sup, when j goes to infinity, fj of yj. But that's the property of being a recovery sequence, that fj of yj, in fact, they converge, that the limit exists. This is f of y. So I've checked that no matter what is y, f of x, where x is the accumulation point of this approximate infimizing sequences, right? F of x is less or equal than f of y for any y. So I have just proved, indeed, that this limit x is a minimizer of f. Okay, so that's the end of proof of 2. And also end of proof of 1, because I proved, indeed, that there exists an x, which is less or equal than any f of y, so x is a minimizer. Okay, so I proved 2 and I proved 1. Proof 3, let x be any point in the argmin of f, not necessarily in k, right? Here, automatically, of course, those xj's were in k, so x is also in k. So I know that, in particular, f has a minimizer in k. Now, it may have many other minimizers. So let's take any minimizer of f. Okay? And let's apply this chain of inequalities for y which equals to x. Okay? Then, in particular, by above, okay, I see that so maybe not in this will be the second step, right? So let me first take the recovery sequence. Okay, so let x be an argmin of f and take the recovery sequence for x. So I take some xj's which converges to x, such that the limit fj of xj equals f of x. Okay, that's the meaning of recovery sequence. But this f of x is the minimum of f, right? Because it's the minimizer. Now you see, I can go exactly through this chain of inequalities, f of x applied to y, which equals to x, and I see that f of x equals to the limit of the infima of fj. So my point is that this minimum of f, in fact, is the limit of the infima of fj. So automatically, the recovery sequence has the property that fj of xj differs from the infimum of fj by a quantity which disappears in the limit. The limit of this and the limit of this is the same. Okay? And that's exactly what's written in point 3 here. If I take a minimizer of f, then when I'm proving it for the recovery sequence, fj of xj differs from the infimum of j, right? Me? You think it's me? Okay. Hopefully now. Right? So this and this differ by something which goes to 0, which is exactly the property 3. So we are done with it. Okay? Maybe questions at this point? Yeah, so this is why I care about gamma convergence. Tells me that if I have a gamma, fj, gamma converge to f, then there is one-to-one correspondence between the infimizing, minimizing, infimizing sequences of fj and the actual minimizers of f. Let me now state a theorem in the context of what we've been discussing before. Okay, so I want to pass here. Definition of gamma convergence, you have these notes. Theorem. So it's a gamma convergence result in the context of those constrained elasticity functionals, which tell you exactly what happens when beta equals to 2, one particular beta. So if, assume that, or let UH in W12 from omega H to R3 satisfy the energy bound EH of UH less or equal than a constant times H squared. Okay, that's the only assumption in this theorem.
Okay, one quick question. So in terms of the convergence, is gamma convergence more rigid or stricter than uniform convergence?
No, because no.
It's much weaker. Would you say it's?
I mean, we've seen examples, right? So it's really, you can find examples when one is and one isn't. So I have UH, okay? So it's really related to convergence of minimizers in terms of if I have compactness, additional compactness, sort of compactness problem. Right? So I have assume that you have a sequence of UHs which converges, which does not, it's not bifunctional converge, such that the energy scales like this. Okay, then the following holds for YH, so YH, which are now W12 from omega 1 to RH. So I define YH as, here again, so I define UH to be YH as follows, YH of X, let's say X prime, X3, right? So this is in little omega, this is between -1/2 and 1/2. As UH of X prime, HX3, and I just subtract the constant. I want to reference the sequence, so I subtract to average of omega, average of UH on omega H. Right? So I only assume the energetical bound, and the following holds for those rescaled sequence of deformations. So property 1, actually YHs converge to something, okay, up to a subsequence in W12 from omega 1 to R3, okay, up to a subsequence. That's already interesting because I only have the bound on the energies, and as we discussed yesterday, this implies the bounds on the L2 norms of the gradients. So it's easy to believe that UHs or rescaled UHs converge weakly to something. But here I say I can get a strong convergence. We converge strongly to some limit. Moreover, 1 over h d3yh converge also strongly to something, to some limit, which I call B in L2, right? So this is the derivatives, d3 by h. d3 by h is like d3 by h. L2 from, okay, omega to R. So this is also update sub C. So this y, of course, I know that it's a strong limit in W12, it says W12. In fact, it's higher, it has higher regularity. So y is in W22, it has 2 derivatives. So it is higher regular than the sequence that it's produced from. And, okay, so it's W22 from little omega to R3. By this, I mean that D3y, right? So here that's a function on the capital on omega 1. It's on omega 1. So D3 of y is 0. So I'm going to equivalently write it as a function, just defined on the midplane. And this y is an isometric immersion of the portion of the metric G, which gives me my functional here. It's first of all restricted to x3 equals 0. I'm just looking at the residue of this metric on the midplane. And moreover, I'm taking only its 2 by 2 component. Right? So this G, what is G at each point? G of x prime, x3, this is in omega h, okay, or omega 1, whatever, in omega 1. Okay, that's given G. It looks like this. It's a symmetry. It's a 3 by 3 symmetric positive definite matrix. So each component of it depends on x prime and x3, and it has a 2 by 2 binary. So I'm taking this G 2 by 2, that's a 2 by 2 minor. I'm only checking what it does on the midplane. And here I claim that this Y, which is automatically of higher regularity than what I had, okay? This Y, which goes from now 2 dimensions to 3 dimensions, is an isometric immersion of the original of that metric. Okay, so how can you think about this Y? You have your omega, 2-dimensional, and Y gives you a surface, Y of omega. This is now sitting in 3 dimensions, say surface. And on this surface, you have tangent vectors, d1y, d2y, and they are such that the scalar products between them is determined exactly by the G, by 2 by 2 minor of G. Okay? Further, B, that B, which was the limit of the normal vector, so to speak, is also higher regularity than expected, not just L2, but in fact it's W12. And it's also in L infinity from omega to R3. Okay, so likewise, the limiting field only sees the in-plane components. It does not depend on the out-of-plane, on the x3 component, normal component. Okay? And what's the property of B? It's such that if I look at the matrix D1y, D2y, so these are the tangent vectors, and I put B here as a third vector. Now this is a 3 by 3 matrix. Okay, I have B somewhere here. So this is something like the normal vector, but in the ambient metric given by G. So this thing at x prime 0 gives me possibly non-symmetric square root of the full prestrained metric G, not just its 2x2 component. Okay, so this belongs to SO3 times G 1/2, okay, x prime 0. You can think that this B is like the Cosera vector, right? That is aligned with respect to D1y and D2y, so that I get the square root of G. Because really, this is what we discussed yesterday. What do I want? When is this 0? This is 0 if and only if gradient U transpose gradient U is G. So this is 0 if and only if gradient U up to a rotation is a square root of G. So here I'm saying that if you have this energy bound, then automatically in the limit, I'm producing something which has this property on the midplate. Not everywhere, but on the midplate when x3 equals to 0. Okay? Point 3, moreover, you see how much information I get just from this assumption, no other assumption. 3, 1 over h squared EH. Okay, that's a functional. Gamma converges to what I call I2. And the functional I2 is defined on y's like this, okay? On W22 isometric immersions of the tangential component of the metric restricted to the midplate. And I2 of y equals to, there is a certain prefactor, 1 over 24, if you know the Kirchhoff theory in nonlinear elasticity, that's the same 1 over 24. And then I have an integral on the midplate omega. Okay, Q2, this is a certain quadratic form. I will explain it in a moment. You can think that this is like the norm square. Okay, the important is what does it act on? It acts on gradient y transpose gradient b, symmetric part of it. This is like the second fundamental form of the surface y with respect to the ambient metric G, in which the normal vector is given by B. Okay? And you compare it with the preferred second fundamental form that in fact can be read from G by means of 1/2 D3G of, okay, 1/2 D3G of, okay, dot, this is the dot means x prime in omega. Okay, so let's write it x prime 0, 2 by 2. Only the x prime because I'm only doing in omega. So here, this is not really, you know, I don't want to overwhelm you with the information, but this Q2 can be computed explicitly out of W. So for different energy densities, we have isotropic energy with some Lamé coefficient, then Q2 is something, okay? You compute it explicitly. There is a formula, so just let me quickly say. So you define, or maybe I just say Q2 is quadratic form that is explicitly given by W. Explicitly, I mean, you tell me what is W, I tell you what is Q2.
One quick question. So the fact that you have scaled it by h square is important. I see. Okay.
It goes to 0, right? So EH, I know that if at some sequence goes to scales like h squared, then EH of UH goes to 0. So it makes sense to divide it by the natural scaling that's assumed here. And then I say that EH over H squared, it has a gamma limit. So the minimizers of this, or infimizers of this, accumulate at minimizers of this. I am not saying that those UHs are minimizers. I'm not saying. Okay? In particular, that they can be minimizers. But I say, if you are able to find the UH with this property, then I can get this much. Of course, for different UHs, you may have different Ys. We'll discuss it later. Yes.
In the, I have a question for the first line. So when you say this, you say that for every H, we have a function UH that satisfies, we have a family of functions UH
Yes.
indexed by H. It's
Yes.
not just one function. And,
No,
and then,
UH.
all,
So
and
this
then
is by
all the
energy.
convergence.
So energies are parameterized by H. H is the thickness of the plate, which goes to 0. Okay? So let UH be, so here as H goes to 0, for each H, I have a UH.
And then all the convergence are in terms of H.
When H goes to 0, of course. When the limit is when H goes to 0, of course. Okay? I mean, up to a subsequence. So there is a lot of information here. It's a very strong theorem. So let me try to explain to you, give you some, at least tell you how you obtain the convergence properties. And they follow from the rigidity estimates that we discussed yesterday. Sketch of proof of convergence. So this convergence property sort of, replaces the compactness that I have here. Here I use the existence of the compact subset of the domain of my functionals on which I define the gamma limit, okay? Only to know, as you've seen from the proof, to know that those xj's have a limit because they are all sitting in one compact set. I don't need it here. Here I know if I prove 1 and 2, okay, that the limit always exists because I'm telling you, if I know that I have this, then up to a subsequence, I have the limit. So these first two properties are called the compactness properties, and then property number 3 is gamma lim and gamma lim. So sketch of proof of convergence, recall the rigidity estimate. So recall that I have, so for every u in W12 from some omega to R3, there exists a rotation in SO3 such that the integral gradient u minus this rotation square is bounded by universal constant times the distance square of gradient u from SO3. Right? That was the Frisecker-James-Muller rigidity estimate. That's a nonlinear version of Korn's inequality, and that's a quantitative version of the Lewis theorem that we discussed yesterday. I feel you have a question.
The question is on the interpretation
Yes,
of the theorem. So, is it what I asked was is it at the end a pure bending deformation? The fact that we have a pure bending deformation.
It's like the membrane energy. This is exactly like the pure bending.
So there is no. Yes, it's grad B, so there is no
stretching. The stretching you obtain, the stretching is 0. You are perfectly isometrically immersing that.
Yes, yes.
And this is the difference. You are quantifying how much your second fundamental form, with respect, appropriately understood, with respect to the pre-strain, differs from the perfect second fundamental form that you read from G, from the pre-strain. Yes, so this is exactly, thank you, that's a very good point. That's exactly like the bending. Okay? I would call it Kirchhoff energy in the classical nonlinear elasticity when there is no pre-strain. Okay? And this is very important to remember. This relates to beta. So here I'm discussing beta equal to.
I'm a little confused with that statement because so when the energy itself is coming from the fact that the Riemannian curvature of the underlying metric is not necessarily 0, right?
So not just yes, the Riemann curvature, of course.
So when you say that it's pure bending, I'm a little confused with that.
What?
When you say it's pure bending,
yeah,
I'm a little confused with that.
No, I'm not saying that this is the best. What does it mean? I'm not saying that this is equivalent. I'm just saying that that's the gamma limit. It can happen that this minimizes to 0. Mm-hmm. 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 There will exist. That's exactly where that is exactly where this is non-trivial. Okay. Because you see here, this is the picture that I had before. This is your omega mid-play. So if this has Gaussian curvature, so maybe that's a good point to make. We've already discussed it yesterday. So this is two-dimensional set. What does it mean that the Gaussian curvature of this, which is equivalent to the full Riemann curvature tensor, is just 2 dimensions, is not 0? It means there is no isometric immersion in R2. But this has nothing to do with isometric immersions in R3. And that is your Y that I am detecting here. In fact, every two-dimensional metric has an isometric immersion in R3 with regularity C1 alpha for alpha, less than 1/3. If the Gaussian curvature is strictly positive, you can even do smooth.
So here, our hypothesis is that there is a sequence of deformation whose energy.
I'm taking any sequence of deformations. Okay, so that's a theorem. Maybe you are going a bit too far. Okay,
let's
just assumption that you have some sequence of deformations, and you know that the energy is like at least h squared.
This is what I meant. There exists such sequence.
Yes.
If there is none,
then there is no theorem.
Yes. So we are kind of assuming some properties of the initial.
You are not assuming any compactness. You are. I don't know what is your problem. Okay, we will see. You will see. As usual, you ask for not going to get anywhere. Okay, so that's a true mathematical statement. I wanted to understand it. There are, of course, many others. Okay, it's the beginning of a very long story. I've written 400 pages book on the topic. So it's just one theorem. So sketch of proof. So that's what we discussed yesterday, Friese-James-Muller theorem. Okay, rigidity estimate, which tells you that distance square of gradient u from SO3 is the error that you are making in your gradient u from one fixed rotation. Okay, so rigid motion. So we are going to look at this plate, omega h. Okay, so that's omega h. So it has a thickness h. And I'm going to, let's make it even longer. I'm going to divide it into cubes on the length scale h. Okay, so this whole thing is omega h. This is h, and this is also h. Okay, so I have little cubes called ui, and I have h square of them. So I write omega h as the union of ui, I equal 1 to like 1 over h squared, right? Because this is this thing is little omega, which is two-dimensional. This thing. Okay, so I divide my plate into small cubes of length scale h. Okay? So on each ui, which is like minus h half cube, okay? Apply, so this, let's call this FJM in honor of the authors, Lewicka, James, and Muller. So you apply FJM on 2, so there's change of variable necessary, UH composed with G of X0 minus 1/2 X. So basically you want to apply this thing on UI, but modulo the metric. So you're taking the square root of the metric at some point X0, so maybe let's write it Xi. So let's let Xi be a center of UI, okay, why not? And then you just approximate the metric on this little cube by a metric that's, you know, constant, just sampled from xi. And here take the linear function, right? That's the linear function whose gradient is the square root of the metric. Then you invert. Okay, so that would be the inverse of the isometric immersion of a constant metric g of xi. So apply this to this okay, g of x0, g of xi, 1/2 ui. Okay, so I'm applying FJM on a cube ui modulo the metric. Now the crucial information is that, of course, this constant here depends on the omega, on the set on which I'm applying it, but it is scaling invariant. It's a nonlinear inequality, so it's not obvious. But yes, it is scaling invariant. Meaning that if you scale omega, if you dilate it, make it small or large by a constant, then it's going to be the same constant, right? Part of the theorem. It's a non-trivial information, but yes. In fact, C omega is uniformly bounded from above and below for any family of omegas which are by Lipschitz equivalent. You take omega, and if you take another omega, and they are by Lipschitz equivalent, then this constant depends only on the Lipschitz constant of the diffeomorphism and on the original omega. Okay. So what do we get? Maybe I pass here. So we get integral on ui, gradient right, minus rotation g of xi 1/2 square. So basically I'm applying this, but modulo change of, right? So if I apply, I mean, you just have to do some calculation by yourself, right? So the gradient of this is the gradient of at that point times this g of xi minus 1/2. Okay, so then you have to apply the change of variable to pass between the ui and between this ui that's been deformed, and that is why I get the following. That's less than universal constant, and here I have the integral on ui, distance square of gradient from g 1/2 at x0, and I need SO3 here. So of course, this is, now I can replace this g inverse 1/2 x0 by g inverse, I mean not inverse, g 1/2 at x, because g is a smooth metric, it's a smooth function, so it has some Lipschitz constant. So on ui, this differs from g 1/2 of x only bound by the length scale h, and here I have square, so I will have h to the power cube. So this is like C integral on ui, distance square of gradient, g inverse 1/2 now at x, right, from any x from SO3, plus, okay, I can even write h square, right, coming from h to the power 2 times the volume of ui. I'm integrating on ui. Okay, so now I want to exchange. So what happened, you see, on each of these cubes, I approximated gradient right, with the error that's directly related. This is like my energy, right? That's the energy, but I'm integrating not on the whole ui, not on the whole omega h. I'm only integrating on ui. And there is a residue here, but they are of the same order, because this is basically like h cubed, because my original energy is h square, but I'm not dividing by 1/h, right? This was the h, and this is like h cubed again. I mean, after I sum over all ui's. Okay, we will see this. So I am approximating gradient UH by a constant matrix. For each I am approximating on UI my gradient UH by a constant matrix with this error which directly comes from the energy. Okay? So now I want to approximate it not by a function, by a field that's not piecewise constant, but it's continuous or even higher regular. So okay, so this was step 1. So now step 2 is modify piecewise constant approximant R G of xi 1/2. Okay, to get BH, okay? BH going from omega to R3/3, okay, such that I have the same. So instead of this, I will have now some field, continuous field. We will see that's defined on the whole UI, and now sum those inequalities. So in the left-hand side, I will get the integral on the whole omega h, gradient UH minus BH. Okay, so BH is something that replaces this. So now on the right, I sum over all i's from 1 to 1 over h squared, and I get the integral on the whole omega h. This is bounded by what? Now this summed over all ui's, this gives me the full energy multiplied by h, because EH is 1 over h, precisely this. So constant h times the energy plus, if I sum this over all ui's, then I get the volume of the union of ui's, but that was omega h. Okay, and the volume is like h. So I get h cubed. But that's exactly h cubed, right? EH was like h squared. So together, both terms are of the same order, namely h cubed. So also, so this B, the H, you know, even originally this was a piecewise constant field. Clearly it's in L2. Now I modified it. It's going to be, you know, some smoothness, regularity. But the crucial information is that this BH, in fact, belongs to W12. It has one derivative more. It has one derivative. And how can I prove, how can I expect this type of estimate? Well, I need to know how this approximation differs from the nearby approximation. So I need some sort of quotient, difference quotient bound on the B, right? Let's call this BI. At BI, which is B at xi, and B at the next nearby cube in my partition. Okay? So how can I know this difference quotient? This again comes from FJM inequality. Namely, you say, oh, now I have 2 cubes. I applied FJM of the first cube. I applied FJM on the second cube, but I could have also applied FJM on the union of those cubes. And then I would have with the same constant, okay, I would have approximation by means of difference rotation or a different fixed constant matrix here. And then I know, but this approximation on a larger cube encompasses approximation on a smaller cube and the other smaller cube that are subcubes of this larger cube. Okay, so you have some BI here, you have BI plus 1 here, but you have another B bar that is good for both cubes. So you check that the difference between BI and BI plus 1 is like the difference of BI from B bar, okay? But they are both related to FJM approximation on the large cube and the distance from B bar from BI plus 1. Okay? So sort of this is how you get to the difference quotient and how you prove that BH has one derivative, and the L2 norm, the integral on omega of the gradient BH, is bounded by a constant. Why? Why? Because you are losing. So you see, here I integrate on omega. So this is like averaging on omega h. So I would have to divide it by h. Then I get hch squared. And I'm losing 1 power of h, because now I am talking about the difference quotient. I'm talking about the derivatives. Okay? So I'm losing 1 power, this is square. I'm losing 1 power of h inside the integration, but here it is squared. So I'm losing 2 powers of h with respect to ch squared that I have here, after I have divided out by the thickness of the domain, which leads to the integral on omega. Okay? So there's a sketch of proof. Hopefully you can believe in that. Okay, so that's the crucial information. You are able to approximate your deformations by a field, matrix field, that lives only on the midplate. Each of them is of regularity higher than original sequence, so regularity of W12, right? Because I'm approximating the derivatives, the gradients, not UHs. And they have a uniform bound for the L2 norm of the gradient. Okay, so step 3, in particular from this, okay, I see that BHs are bounded in W12, so up to a subsequence, they converge weakly to some limiting field. Okay, and what can I say about this limiting field? Okay, 1 over h of this is like h squared, so it converges to 0, but gradients of UH get closer and closer to the square root of G, okay? Because that's the energy. So the same is true for the approximating sequence BH. So in the limit, this B is in S of 3 G x prime 0 1/2, right? Because that's the limiting property of UH, of the gradient UH, that I read from the energy. Then, what can I say about my frame? D1YH, D2YH, and 1 over H, D3YH. Okay. So BHs converge to B, and D1H, D2H, these are just rescaled versions, right? I'm rescaling to take the integration on omega 1 rather than omega H, right? That was my definition of YH. I'm rescaling everything to the universal domain of thickness 1. So D1UH, which is like D1YH, but after the change of variable, and D2UH, these are like B, you know, the first column and the second column, so this converges to B, okay, here and also here, because this is like D3UH, but now I am rescaling to omega 1. Okay. So, and this is the convergence in L2. Okay, why not? I have convergence of BH in W12, but I only had convergence. So in particular, that's a convergence in L2, and I had only L2 convergence of this from the energy. Okay. So anyways, this converges for sure to B, but this means that the structure of B is like D1 sum Y and D2 sum Y, and I'm calling the third column, which is the limit, I'm calling you the B. That will be the B that I have there. Because if the YHs converge, okay, if the derivatives converge, then automatically the limit must also be a derivative, right? It's always like this. So So that's the structure of B. So therefore, I know that YH converges Y, right? That Y. And Y must be in W22 because, well, gradient Y converges, gradient YH converges to gradient Y, but that's a part of B, okay, that is higher regular because it's W12. So here I had a convergence in W12 because I had the different quotient estimate. So B has one derivative, but the elements of B are derivatives of Y. So this means that Y has two derivatives. Okay, so this is how I get this augmented regularity. I get the two derivatives on Y, and I also get from this B being square root, okay, non-symmetric square root of G. I get, in particular, the other two conditions, right? So in particular, gradient Y transpose gradient Y equals 2G 2 by 2, X prime 0. So that's the proof of convergence, of compactness, convergence of the fields. The corollary of the theorem, so that's corollary of my main result today. Is that the infimum of the H scaling like H square is equivalent to the existence of W22 isometric immersion of my metric G restricted to the midplane. Exists W22Y, such that gradient Y transpose gradient Y equals to G X prime 0 to Y. Because on one hand, if the infimum is scales like H squared, then there exists a UH such that this, and I get this. On the other hand, we have the gamma convergence result, so I can use the recovery sequence. Okay, so if there exists some Y which is as we've written in point 2, so then this energy, okay, is finite at this point. To take its recovery sequence, this will give you the sequence of deformations, okay, which recover Y, in particular their energy scales like H squared. Okay, so this is if and only if condition.
Marta,
Yes.
the constant C over there, is it the domain that you have has always been bounded, right? Is there any statements on how the scaling with the volume of the domain is, with the constant? So you,
The volume of the domain. So the domain is omega H always, thin plate,
yeah,
right?
but if I were to now, all of this has been in the limit where you're taking the thickness to 0,
yes.
keeping the volume finite.
The mid plate is two-dimensional.
Yes, the two-dimensional area finite.
Yes.
Are there refinements on this that one can now do where you take the size of the domain to become infinite? And
also, the other direction, instead of plates, you can do rods, rod theories, right? No, so, and the other way around, well, I'm not aware, but this can be done if there is interest.
Then I can be FJM inequality where you said there was scale invariant.
Yes.
Are there statements about the constant being scale invariant over here?
About the content.
The constant, the C.
No, but that's just no. The point is that there exists a C, but I'm not sure what you mean. So this infimum must be of the order at least H squared, okay, no matter what is the constant. So now you are asking, assume that I have an isometric immersion. can I say that the infimum is like h squared, and what's the constant here? Can I compute it?
Or can you say something
I
about how the
make-
constant changes as you make the domain bigger or smaller?
I cannot say right now, but I could say if I thought about that. Okay, put it like this. Okay, so maybe that's a good point to stop. That's an important corollary. We start from it in my next lecture, and we will see what we can do with. So that's the theorem for scaling h squared. Okay, so that's why maybe I just say this is h squared. This membrane theory means that I have no wrinkling. Right? Means that in the limit, I see one nice surface, nice meaning of regularity W22. Maybe it's not, very nice for you, but at least it's a surface. It's one surface. So I have a convergence to films, to something that's just a thin film around this mid surface Y, which is the minimizer of the gamma limit. So we know what happens at the scaling h squared. So in my next lecture, I want to show you what happens above. It's somehow this square, this beta equals 2 is a critical value. What I can say, and as I said, I can say anything I want about beta greater than 2, and what I can say for beta less than 2. And we will see that still I can say something for beta less than 2. Okay? So maybe that's a good point to stop, unless you have questions.
Yes, I have one. So maybe it's a trivial one. So the space where H is defined over lowercase omega or Y. Sorry, Y.
Yes.
It is defined here. It is defined over
Yes.
omega, but here there is a convergence of YH, and YH is defined over capital omega, over the thick.
Right. So YH. So what is very good? So what is this convergence? This is convergence. As actually we can pass here. I explained. So this is convergence in W12 on omega 1. YHs are, so UHs are defined on omega H. I rescale them. This is, X prime H, X3. I rescale them, taking, I have to write mathematical truths. I'm hiding a lot of things under the carpet. Anyways, they are defined on omega 1. So that's true that YHs converge from, in W12 as fields from omega 1 to R3 to something, to some Y.
Yes.
But it turns out that the D3 of Y is 0. Because 1 over H, D3YH, converges to something.
Okay.
So it means that D3YH converges to 0. Okay? Because I proved that.
Yes.
So in fact, you are perfectly right. At the face value, this Y is a vector field from omega 1 to R3. However, its D3 derivative is 0. So I interpreted it as a field from 2 dimensions to R3. Okay?
The CH square condition. So it is a condition on G, right?
No, it's the condition on UH, right? Here it's
But I mean,
CH of UH. You have a sequence of deformations whose energy scales like
that
X
will
squared.
depend on, whether such a sequence exists or
Yes.
not will depend on the nature of G.
Yes, here,
For example, yeah.
exactly. This is what, when it tells you when it exists.
There, when you were saying about the bounds with respect to the Riemann curvature,
Yes.
that is where we don't have.
We will discuss it next time. We have to stop now. You are completely correct. This is, at this point, that's the equivalent condition when such sequence exists, namely when the infimum of the energy scales like H squared. That's equivalent to, and that's a condition on the metric, you are right, to existence of W22, isometric immersion of a metric. So when it exists, when it doesn't exist, you have to come to my next class.
Very quick question, maybe related to that, is so the gradient in the direction, the thickness direction, somehow is bounded by some thickness to power something. So I didn't catch that completely.
At which point of discussion?
In this point, where
Yeah.
you have the gradient of U along the, let's say, in the thickness direction.
So here I'm just on UI. UIs
This is the-
are small cubes. This is not rescaled. This can be anything.
Yeah, but
It's just gradient UH.
so maybe so my question is, so there is some constraint on the shear deformation along the thickness, which is why you're sort of in this Kirchhoff limit, right?
Effectively, I'm proving that
You don't
this
have-
this smallness of energy implies that in the limit, yes, that you only see that what happens. So maybe this will help. How would I didn't talk about the gamma convergence, right? How do I find this UH, which is the recovery sequence for my energy? I would take Y, so I tell you what is UH, how UH, which satisfies this bound, how it looks like, okay? So you take your Y, so this is omega H. Okay? So first of all, you have omega two-dimensional guy here, the mid-plane, and it's transformed by one W22 regular field, so this is Y of omega, okay? And then the E3 here, direction, this will be transformed in the direction of B, of this Koserat vector. Just do the Kirchhoff-Love-Ansatz, okay? And you have some warping, it's not exactly Kirchhoff-Love-Ansatz at the leading order term. Then you have some warping, but it's of lower order. And this is how you get, this is how you get your thin shell. I don't know if that answers your question.
But my question was, what is the, so E3 becomes B, and so
Again?
so in the drawing that you have written, right? So E3 becomes B, but along the thickness direction, there is also small changes in B along the thickness direction in the transformed state, and there is
No, it's not. It's a unit normal in the ambient metric. In the ambient metric with respect to this pre-strain metric B, pre-strain metric G. So B changes at each X, you have a different B. So B is just of regularity W1, 2. It's not a normal vector. It changes along the omega, along Y of omega. And this is where you are sending your normal directions. That's what you get from the theory. Okay, you can talk later.
You may send the normal to something, I mean, you may send E3 to something that is not normal.
You have.
And this has an energetic cost that is lower than CH square.
That's exactly
Yes,
what happens.
if I can,
exactly what happens at H square.
Yes, when we derived, I mean, for those who were here last week, when we derived the bending modulus of a plate, it scales like H cube, but this is because EH has been rescaled by H1.
Very good, exactly. That's why we have the bending. Yes, exactly. Only that now it is done, precise without any assumption. You see, here you are not making any ansatz. Here you are proving that the ansatz is given from the first principles. That you only start by EH, which is a three-dimensional non-Euclidean elasticity, not making any assumption, any ansatz. And it shows you that at different energy levels, in particular here at H square, you are recovering, in a sense, what I understand you had as an ansatz in the previous classes. Yeah, so you are proving, in a sense, that the ansatz is correct in that energetical. At that energy level, at different energy levels, it will turn out that we have something else, and the gamma limit will be something else. So you will have a hierarchy of the limiting theories. In fact, you will have an infinite hierarchy of the limiting theories. This is what we will do next classes. Okay.
So if we had, for example, H cube, or I mean order higher, then we'll end up,
You will see, yes. So if that is, if this is in fact h cube, it's not possible. H to power 4 is possible. Then in particular, okay, of course, if something is less than h to power 4, it's less than h squared. So you will have this, but this will be trivial. This will minimize to 0. And when this minimizes to 0, it will turn out that minimizes on the unique, automatically smooth y and b. So then in your recovery sequence, you will have that y and that b, and you will be seeing gamma limit with respect to that y and that b and capturing higher order effects. That is the passage from h squared to h to the power 4.
incompatibilities which are not surface incompatibilities.
Not what?
I mean, so the two terms that we are getting here, one of the term stretching is identically satisfied.
Yes.
And the other energy that we are seeing right now is
Bending.
is not satisfied.
Yes,
These
but
are
in
both
higher level, you will start seeing stretching of the higher order.
Of
course, you will see there will be the whole, it's like a network, not just a higher level, but a network of theory. So we'll be seeing both stretching and bending with respect to what. You will see curiously other terms, not just stretching and only bending. There will be another term that is not present in the classical elasticity, where G is identity, so there is no curvature, no nothing. You will see extra terms, extra with respect to the stretching and bending that capture curvatures at appropriate orders, you know, tailored to the energy level that we will be discussing. At the moment, this is just h squared. Good? Okay. Thank you.